Hello, good day. My name is Adrian Prasad, and today I'll be discussing my reimplementation and extension of the paper Deep Leakage and Gradients. The motivation for this work is multi-party computation. Modern ML and AI applications are extremely distributed in nature, requiring training on many machines, requiring data from many parties, and requiring a great deal of sharing between the parties. Many tasks today are collaborative in the ML and AI space. However, data must remain private in many applications. Think of hospitals, for instance, sharing patient data to figure out stuff such as comorbidities. The question that the work that I'm going to explore really begs is it safe to share models, weights, and gradients arbitrarily? One might think you can't really extract data from the weights or gradients. However, that's what we seek to question. The threat model for us is gradient leakage. You can think of many parties sharing gradients and weights to some type of code base. And then an end user can pull those gradients and weights and perhaps train and share back to the code base to continue building your model forward. However, a malicious entity could decide to take the gradients and weights and try to reconstruct some type of data from that. So you can think of it as perhaps private images, financial information, personal data, anything of the like, and just grabbing it, reconstructing it, and that data was supposed to be private. So that's the threat model that we fundamentally seek to work with. In this paper, DLG, a simple algorithm is offered to reconstruct data by using the gradients. You simply generate a random dummy data, you pass some iterations over, you get the gradient from the Ashram model that people have posted. You compute your own gradient on the dummy data. You compute the difference between the gradients and your dummy gradients, take the mean square of that, and then do backpropagation with some optimizer. And you keep doing this process until you get something close to the original data or even the entire original data. So the motivation for this implementation is, does this method work? Is it straightforward to implement? And furthermore, in the paper, there's a lack of discussion optimizers. How can they affect the performance of DLG? And this is our extension of the paper. While working on this, it seems that it was pretty straightforward to get a successful reconstruction. Here's after only 100 iterations using LBFGS, I was able to fully reconstruct a 5 from the MNIST dataset. While also working on this, I decided to ask, how do optimizers affect it? So as you scale the batch size on your training, it becomes harder and harder to fully reconstruct the original input. It seems that Adam is very resilient on this limited dataset, while the R models such as SGD and LBFGS seem to not perform as well. Additionally, as you scale hidden layers, it also becomes much more difficult to reconstruct data. And changing optimizer really does have a good effect. Like LBFGS, for instance, perfectly reconstructs the data. SGD and Adam seem a lot less resilient. SGD in particular completely breaks down. So after working with these models and finding out that the optimizers really affected, there were a couple other realizations. Firstly, DLG is pretty quick. It's not incredibly resource intensive. And that means that if this is really something that people would like to maliciously do, people with very limited resources can do it, or with a simple botnet, for instance. In this small study, additionally, optimizers seem to greatly affect the reconstruction. Different optimizers seem to be suited to different tasks, and the model complexity and batch size destroys reconstruction after a certain point. Because as you scale these things up, the complexity becomes far too much for a simple algorithm like this to reconstruct. So that was the entire premise of my work. Thank you for watching.